All right, chapter 7, so 7.1, functions and rate of change. One of the key concepts in calculus is finding the slope of a curve at a point. Okay, our slope is traditionally for a straight line, so keep that in mind. This is understood to mean the slope of a line tangent to the curve at a point. Tangent. Little trig vocabulary here. Because of this, it is worthwhile to review the slope and equations of linear functions. Recall the slope is a numerical measure of the steepness and orientation of a straight line. We're talking about a curve. Geometrically, this may be interpreted as a ratio of rise over run. So all these notations here represent your slope. M is rise over run. The triangle y, triangle s, that's read as delta y over delta x. Delta is another name for the change in y's over the change in x. Subtract your second, your y sub 2 minus y sub 1, x sub 2 minus x sub 1. And if you notice them in the graph, hey, wait a minute, it builds a right triangle. And this angle here to this line is tangent is opposite over adjacent, and that's why we call it the tangent line. So we're going to look at how we find this tangent line with respect to a point on the curve. So first, let's do some graphing. Finding the slope of the line. Okay, so second y minus first y, second x minus first x. Negative 5 minus 1 is a negative 6. Negative 2 minus 2 is negative 4. That becomes a positive 6, 4. Two negatives make that a positive, and we can reduce it to 3 halves. Okay, graph the 2 points. All right, let's graph 2, 1. There's that point. Negative 2, negative 5. There's that point. Slope was a positive 6 fourths. After you simplify the signs, up 6, right 4, there they are. But because you reduced it, we can go up 3, right 2, up 3, right 2, up 3, right 2. Find more points, plot line. Probably remember all that good stuff. B, you should recognize something here. Notice that the y coordinates are the same. That means you're going to get 0 in the numerator when you subtract the y's. They're up. Negative 3 minus a negative 3 changes that to a plus. They're opposites, you get a 0. X coordinates are different. Doesn't matter what that value is as long as it's not 0. Your slope is 0, which means you're going to get a horizontal line. If I plot 5, negative 3, negative 2, negative 3, draw my line, there it is. So the same holds true, keep this in mind, if my x coordinates were the same. Then I'll have a 0 on the bottom, and then it's undefined. That would represent a vertical line. All right, so the equations of our line, okay? To write the equation of a line, you have to have slope and you have to have a point. You have to have these two. Now, they say that the point is x sub 1 comma y sub 1. Now, the most popular equation of a line is slope-intercept. It's probably tattooed somewhere in your brain cells. However, not the best to use because notice that the point provided is the y-intercept. This point, x sub 1, y sub 1, represents any point on your xy coordinate plane. This point restricts you to the y-axis only. Kind of restrictive here, but that's the one everybody seems to know. Not the best to know. All right, so here there's going to be 3 forms of the equation of a line that you will have to know. Second form is standard form. This is kind of old school because it's written as capital AX plus capital BY equals capital C, where those 3 coefficients, capital A, B, and C, are traditionally integers, no fractions. And you can find the slope from this really quickly. It's going to be opposite of A over whatever the B is. Include that sign. So if you think about changing this into y equals mx plus b, you would subtract over the ax, divide over the b, and that's where the slope comes from. And also think about your x and y intercepts here. If I'm looking for an x-intercept, the y-coordinate is 0, and if you plug in a 0, this term zeroes out, so cover it up and solve for x. Divide over the a into the c, there's your x-intercept. So like I said, call this the cover-up technique. If I want to find the x-intercept, cover up the y term. Want to find the y-intercept, put 0 in for x as I cover it up, solve for b. All right, let's look at an equation. Negative 4x plus 3y equals 12. This is standard form, and the first thing you should notice is that we can find the slope right away. Opposite of negative 4 is 4 over 3. There is my slope. Next, you can find your intercepts rather quickly. If I want to find the x-intercept, cover up the y term. -4 goes into 12, -3 times. Cover up the x term. 3 goes into 12 4 times. So -3 comma 0, 0, 4. So if we plot those points, there we have it. And we can draw in our line. We have 2 points. Domain and range for every single line that has a slope that is non-zero is going to be all real numbers for both domain and range. Now, B is in standard form, but this time it has a 0 here. So if I tried to think about finding my x-intercept, which would be a 0, and my y-intercept, which would be 0, divide by 2, divide by 4 into 0, you would get the origin, 0 and 0. I don't have 2 points. So here, yeah, we can still find our slope the traditional way, -2 over 4, or you can solve this for y, subtract over the x and divide by 4. There's my -1/2 for my slope. Now my intercepts was just, like I said, the origin, so I would need to plot the origin and then go down 1, right 2, draw my line. Again, domain and range, all real numbers. Here's y equals 3. It's a horizontal line. There's no x in the equation. I'll never cross the x-axis. Slope is 0. Intercept will only be the y-intercept at 0, 3. Domain will still be all real numbers, but the range will be just in braces 3. There's the only listed value, 1. One number, 3. So you use set notation. And like we said, there's my horizontal line. You have your y-intercept. Pick any other point, left or right, draw on your horizontal line. The next form of the equation is going to be point-slope form of the equation. Point-slope form of the equation. This is the equation that is the most powerful because this fits that definition we talked about with the x sub 1, y sub 1. But a lot of people forget about this one, and this is yet the most powerful. And to believe it or not, you know this equation. And I can't believe, if you tell me you don't remember it, I'm going to probably say you're fooling yourself, or you just didn't have a really good algebra teacher, because watch the magic right here. Watch what I do to this equation. Are you ready? Here we go. I'm going to solve it for m, and I know what you're thinking. Looky there, folks. It's just another version of the slope formula. So if you knew the slope formula, you knew the point-slope form equation. Nobody just overemphasized it for you. So we're going to use that a lot. All right, so find the equation of a line in all 3 forms. All right, so if I'm going through the point -2, -3, x sub 1, y sub 1, and I have the slope, I hate to tell you this, I'm not going to y equals mx plus b. I'm going to point-slope form. Y minus -3, change the sign. Slope equals -3/4 times the binomial x minus the x-coordinate, -2. That's a plus. There it is, point-slope form. You are done. That's 1. All right, now, oh, well, if you want to put it in y equals mx plus b, then, yeah, we're going to have to solve for y. Distribute the -3/4, but if you notice, this denominator 4 is not going to divide evenly into this 2, and you're going to have fraction work. Don't go there. Go to standard form. Because if you're given the slope, -a over b is equal to -3 over 4. So a is 3, b is 4. So I'm going to write my standard form, 3x plus 4y equals capital C. I got to go find c. Then take the point, -2, -3, plug it in for x and y, -6, -12, added together is -18. I put that in for c right there, and there's the equation in standard form. Look, no fractions. Now I take standard form, subtract over the 3x, divide everybody by a 4, reduce by 2, and there's my equation in slope-intercept form. See, if I would have went to here, I'd have to work with fractions, and I really have no desire to work with fractions. All right? Next, B. Oh, now we have to go find the slope first. Okay, 6 minus negative 3, that's 9. Negative 1 minus 2 is negative 3. There's my slope, negative 3. Pick a point. Doesn't matter which one you use, they're both going to work. I chose the first one. Y minus negative 3 is plus 3 equals my slope, negative 3 times x minus 2. Now there's no fractions here. I'll be more than happy to take this point slope form and distribute the negative 3 and solve for y to get it into y equals mx plus b form. So multiplied in the negative 3, subtract over the 3, there's y equals mx plus b. And now standard form, I'll just move over this x term, thank you very much, add it over to the other side. There's standard form. So the two ways you should do this is that if this slope doesn't multiply in nicely, you go to standard form, then to y equals mx plus b form, slope intercept. If the slope multiplies in nice and there's no fractions left here, then go to slope intercept, then to standard. All right, average rate of change. Okay, here the definition, it's nothing more than a slope, but it's given to you in function notation. So here this interval closed interval from a to b, this is x sub 1, this is x sub 2. So this is your second x, this is your first x, and you can see them being subtracted at the bottom. Your f of b is going to be your y coordinate when the x coordinate is b, so that's technically your second y coordinate. And then y sub a, this is when a is plugged into the equation to solve for the y coordinate. So they're going to give you the two x's, but not the two y's. We'll have to find them. All right, let's look at an example. The population in the Metro Phoenix area in 2022 is approximately 4.62 million people. This is up from 3.73 million in 2011. Find and interpret the rate of change in the population. If we assume that a linear relationship, what would be the projected population be in the year 2030? Okay, so my first point is going to be the earliest year. I always like to choose the oldest year or time to be my first point. So 2011, 3.73 million. Second point, 2022, 4.62. Let's go find the slope. 4.62 minus 3.73 all over 2022 minus 2011. That's over 11-year period, 0.89 million, which is 890,000. All right, so that's 0.89 million people in 11 years. All right, so there is my slope. Now, let's make an interpretation of what that means. Well, if I divide 11 into 0.89, I get 0.080909 repeating. That's 0.0809 million people per year that the Phoenix area is growing. Now, if you want to find the population in 2030, there's two ways to do it. You can start from the most recent year, 2022 to 2030 is 8 years. So 8 has to be multiplied to my unit rate right here, and then added to that previous population, I get 5.267 million people by 2030. If you want to use the very first year, then 2030 is 19 years after 211, so 19 times again your unit rate, and then add it to 3.73, you still get the same answer. Example 5, the graph shows approximate annual federal spending for healthcare in billions from 1970 to 2017. Here, Y represents billions of dollars and T represents the number of years after 1970. Find and interpret the average rate of change in spending from the year 2000 to 2017. All right, first things first. This is a terrible graph. Have you ever heard of 1,000 billion, 2,000 billion? No. This is a bad graph. This should be 1, 2, 3, 4, 5, and this should say trillions. Terrible graph. This is what governments like to do to show you, oh, spending is only in billions. No, it's in trillions. All right, let's interpret our numbers here. So 1970 means T is equal to 0. 2000, that'll be 30 years after 1970, so t is 30. In 2017, add 17 to my 30, that's 47. So notice those are your x coordinates on these 2 points. Then we'll take our 2 y coordinates. All right, so here f of 47, that's going to be the second y coordinate minus my first y coordinate of 1,329.4 when x was 30. Just finding the slope, opted to write this in function notation so you can see we're reading it off the graph. We get 2,282.6 divided by 17, which is 134.27 billion per year. Wow, it's a lot of spending. All right, now we're going to consider another idea of finding this, what we call the secant line. And we're going to talk about the difference quotient, which is, again, nothing more than the slope. But everything here is in function notation. So you start with one x coordinate. Point P is at x comma f of x. Then you add h to the x. Here's the second x coordinate, q, and the x coordinate is x plus h, and f of x plus h is my y coordinate. And this secant line, finding the slope here, is going to be, again, your average rate of change or your slope, but we're going to turn it into an expression, which is our difference quotient. Now, h, we don't want it to be 0. That's what it says for the difference quotient, because when we do the slope, you're going to see that it's going to fall. We don't want into the denominator. So, a little visual here for us. Here's a graph. Built this in Desmos. And so what I'm pointing out is here's my point, and here's my h value. As my h gets bigger, notice that the slope of this line does not represent this curve. So the idea here is to make your h smaller and smaller, and notice how the line starts getting closer and closer to the curve. So if your h is getting really, really small, pretty soon that straight line is going to appear to go right over the curve, and now that slope of that secant line is a good representation of the slope of that curve at that point. And all of a sudden notice the line disappeared because now my h is 0. And if h is 0, right, let me put it back at 0, see if I can hit it again. Right, move over there. You can see h, whoop, negative 0.1, let me make it 0. Once it's 0, your slope will be undefined because h being 0 is in my denominator. All right. Okay, so let's go to difference quotient.